So in this lecture, we'll start with CTAT design. So in order to develop a band gap reference, we should have a CTAT as well as PTAT. So in the previous lecture, we discussed about quantities or circuits having opposite temperature coefficient. When added together by proper weighting or by proper scaling, we'll get some result which displays a zero temperature coefficient or a voltage which is independent of temperature. And this is the equation what we have written: Vref equal to alpha 1 V1 plus alpha 2 V2, which will give a band gap reference or a zero temperature coefficient behavior. This is what we discussed. Now so we'll start with CTAT design. CTAT design, CTAT is nothing but circuits which show negative temperature coefficient or voltages which show negative temperature coefficient. Among various device parameters in semiconductor technology, the characteristics of diodes or bipolar junction transistors are the most reproducible and well-defined quantities that can provide positive as well as negative temperature coefficient. So in order to get CTAT as well as PTAT behavior, we will be designing circuits based on diodes or BJTs. So both diodes as well as BJTs can be used to get the behavior of negative temperature coefficient as well as positive temperature coefficient. So we'll start with the CTAT design. So CTAT design is nothing but as temperature increases, voltage will be reducing. Yeah. So for that we'll consider a very basic circuit, diode circuit, where a current source is connected to a diode and where this current source is I0. So don't ask the question now from where will you get this I0 current source. We'll replace those current source, or we'll come to the final circuit, then you will know that you will be knowing that we will not use I0. This I0 is actually the golden reference current that will be designing using a circuit which can generate current by its own. Right. So now so I0 is a current flowing through this diode, and if I measure the voltage across this diode, which is nothing but Vd, if you plot Vd as a function of temperature, that is temperature versus Vd, what you'll get is this Vd behavior is nothing but a CTAT behavior. It is complementary to absolute temperature. The behavior is CTAT, and generally it will show a slope. We look at the values little later, or you can the value will be almost minus 1.6 millivolt per degree temperature when it varies. Yeah, so now the question is why this diode is showing a CTAT behavior. So if you look at the diode current equation, now I0 is a current flowing through the diode. When I write that current equation, I0 is equal to Is into e to the power Vd by Vt, or sometimes we will write it as eta Vt, where this Vt is actually the thermal voltage. So there is some temperature dependency. So this is the thermal voltage. We know that is 26 millivolt at 300 Kelvin. Now we are interested to know how this Vd responds. So from the diode current equation, again Is, yeah. So what we can do is I can write I0 by Is as e to the power of Vd by Vt, or I can write Vd as Vt ln I0 by Is. So this is the equation for Vd. Vd is the diode voltage which is given as Vt ln I0 by Is. So when I directly look at this expression, you can see two quantities here. One is your Vt, the second is ln I0 by Is. So if you remember Is in your semiconductor device physics classes, you would have studied Is is something which is proportional to um, some constant into T. If you carefully look at that, you'll get the exact relation. So since Is is in the denominator, the second term is nothing but which will show a complementary to absolute temperature behavior. But the first term Vt, which is the Kt by Q, which shows a proportional to absolute temperature behavior. So if you look at the diode voltage, there are two terms, one having a dependency proportional to temperature, the other having a dependency complementary or complementary to the temperature. But whenever you plot diode voltage versus temperature, you will definitely get a CTAT behavior because this term is actually strong in this case, or the diode voltage will definitely show a CTAT behavior because the ln I naught by Is term is actually strong here because of the strong dependency on temperature of this Is term. This diode voltage will always show a negative temperature coefficient dependency, and if you measure that, so I can write this term as dou Vd by dou T, which is the slope of this graph will be minus 1.6 millivolt per degree Celsius. So actually we can analyze this in a bit detail, and we can conclude that even though we have two terms here, a diode voltage as a whole will show a negative temperature coefficient dependency. So that proof I am leaving to you. You can do that. Otherwise also you can try this in lab in Cadence, and you will come to know that when you take a diode and pump a current of I naught, and when you plot Vd versus T, it will definitely show a CTAT behavior because of the strong dependency on Is term. So this we can take it as a CTAT. So if you want to get a complementary to absolute temperature behavior, you can simply take a diode, pump a current, plot the voltage, and Vd will be CTAT with a slope of minus 1.6 millivolt per degree. That is the dou Vd by dou T. Now the next question is how to get PTAT. So we'll see how we can get a PTAT behavior, or how will we do PTAT design. Again, as we discussed just before, in order to get the temperature, a proper temperature coefficient, well-defined quantities to provide positive and negative temperature coefficient, diodes are or transistors are the best devices. So we'll again go ahead with some diode circuitry only. So from the diode equation, Vd equal to Vt ln I naught by Is, we have seen that this term, the second term, which is a strongly temperature dependent term, this is a strongly temperature dependent term, that is why it is showing CTAT behavior. But we have seen one term here which is Vt. If I write for Vt, I can write that Vt is Kt by Q, or simply Vt is proportional to temperature. So if I can get this Vt term, so if I can extract this Vt term from this diode voltage, definitely I'll get a behavior which is proportional to absolute temperature. So what I can do for that? How can I extract this Vt from this behavior? So what I have here is a circuit, the previous circuit, where a diode is connected, pumping a current I naught, and this is the Vd voltage. Now, in order to extract Vt from this particular diode equation, what I am doing is I am taking another circuit, pumping a current I naught. Instead of connecting one diode, I am trying to connect two diodes, or you can use many number of diodes, say D1, D2, and say you have n diodes, say it is Dn. Now voltage across all the diodes are same, there is no doubt in that, right? The voltage across all the diodes are same, and I'll mark this as say VD1, some voltage. Now current through any diode, as we have written, I is equal to Is into e to the power Vd by Vt. That is a current through a diode. Now that is a current through a single diode. Now we have the total current here is I0, which is divided among n number of diodes. So I can write I0 is equal to n times I, or I can write I0 is equal to n into Is into e to the power Vd by Vt. Sorry, it is not Vd, it is Vd1, because I am marking this voltage as Vd1. So I can write I0 as n into Is into e to the power Vd1 by Vt. From this, if I write Vd1, Vd1 is nothing but Vt into ln I0 by Nis. Yes. Now from this circuit we have written Vd equal to Vt into ln I0 by Is. So this is a trick here. In order to get a PTAT, or in order to extract Vt from this equation, what I'll do is I'll consider this as equation number 1, this as equation number 2. I'll simply write Vd minus Vd1, or if I can do Vd minus Vd1, what we'll get? Vt ln I0 by Is minus Vt ln I0 by Nis. So what will be the result? I'll use black color. So Vd minus Vd1 will be equal to Vt ln n. So where Vt is actually Kt by Q. So ln n is, this is a constant value. So a constant into Kt by Q, which is exactly a PTAT. So this is a PTAT, right? So from a single diode circuit you got CTAT. Now when if I can get Vd minus Vd1, so this PTAT is possible. PTAT is possible from Vt, which is the thermal voltage which is proportional to absolute temperature, and that can be derived from the difference between Vd and Vd1. So that will definitely give you a PTAT design. Now the question is, how will you do this Vd minus Vd1 so that you will get a PTAT? Already we have a CTAT there. So then how will you combine this to get a BGR? So that is the rest of the thing. So since we understood how to get a CTAT and PTAT separately, we'll see this in next class, next lecture. Thank you.